All right. Hello. Today we are talking about bugs of unstructured state. In a previous talk, we talked about code rot, code smells, and common software defects. And I mentioned there are stateful code smells, and that three groups of smells stand out in particular. Today's talk is about bugs of unstructured state. Software gets really fascinating when it's used to measure the outside world, and when code can perform interesting business logic. For example, when embedded software engineers program the hardware drivers to use sensors to measure qualities, position, time, humidity of pressure, or electromagnetism. And these are values that change, and efficient embedded executables will rely on these sensors to perform desired behavior. So suppose you're building the embedded software of a multimeter, and you're programming the calculation of measuring current across a wire. And suppose you're building this tool in the 21st century with capacitance and resistance sensors, supporting floating point outputs on a circuit board with access to an arithmetic logic unit. And you already have the measures for voltage and resistance. V equals IR. So if you want to measure the current of the wire, then you would divide voltage by resistance, and kaboom, you have made the most famous error in all of mathematics, divide by zero. For whatever reason, you risk a stupid explosion if your denominator is zero. And for real, this has once halted the operations of a US naval battleship in the 70s, causing the ship's propulsion systems to fail, making the US Navy very suspicious of uncommon denominators. Type errors are common in languages without strict type safety. JavaScript, Ruby, Python, and even the Bash shell lacks proper types. And yeah, some of these languages are somewhat type safe-ish. They have duck types. But folks, we are duck hunting. And if it acts like a duck and it quacks like a duck, it's probably a duck or a guy with a duck call. Because industrial strength software demands data contracts, and type safety assures against software defects like functional programming does. And many modern programming languages use their type systems to enable kick-ass language features, such as IntelliSense auto-completion or compile time code validation. The right tools can help prevent most of these bugs at compile time, and type languages do help a ton. And so does linting and coverage requirements. But even still, most linters won't prevent you from making index out of bounds errors and key not found exceptions. And these are what happen when you make the wrong assumptions about state that is unstructured, because arrays are not guaranteed to have a zero indexed element, and maps are not assured to have every key. Knowing is half the battle, and unstructured state is ignorance. Developers cannot rely on faith alone. Inbound data is shaped correctly. And the communication between microservices or across networks are delicate operations. A rookie architecture mistake is allowing separate data contracts across services. This usually happens when software is built with different languages or frameworks. And carefully coordinating these interfaces seems like the approach at first, but soon means every update or change takes twice as long, and the copy pasta begins to leak. And just because services are communicating doesn't mean the communications are correct. All services need to validate input and ensure sane behavior. This is where so many security bugs come from: input validation. Maintaining assured data contracts is very challenging and requires architectural discipline, but is required to conform input shape to reliable single-purpose data structures. So here's the rules of thumb. As a value will be read and used in business logic, you want to be sure the values you're getting back are trustworthy. And if the value will be written out to disk or database, you definitely want to see your inputs that construct that value are validated. Can you trust your type system? Do you expect your numbers to be null, negative, or even integers? And if the value will be executed, are you sure it's code and that the code compiles and it's going through the correct interpreter? And why are you executing that again? What is the source of truth of that code? Do you have a source of truth? You don't have a source of truth? Unconstrained input proms are part of input validation. In this case, the data is correct, but the size and the time and the place are not. You ever see those warning signs on medicine or products that make you go, well, yeah, duh. Unconstrained inputs are why these problems exist, in large part because humans are wonderfully creative and terrible. If you ask your new user to provide an email to contact them, they will give you the entire text of Moby Dick at hotmail.com. If you request an image avatar of any file type, they will upload a strobing GIF or a 1x1 white pixel or 4K pornography. If you're a terrible software company, you might ask your users to zip up their entire code base into a compressed tar file and upload it to a shitty IBM cloud to be scanned for mistakes in software design. After all, how big can a code base be? The same goes for software outputs as well. If your API returns a list of items, does it return those items paginated? Unbound data shapes will quickly crash machines that can't handle the sheer multitude of results. Does Twitter have an API endpoint for give me all the tweets? Of course not. You want all the tweets? You can't handle the tweets. And so these are the bugs of unstructured state. The common denominator is the input is unknown or wrong or unvalidated or zero. These are the defects that emerge particularly when working with IO. Many security vulnerabilities are found by exploiting unstructured state bugs. Adversarial input shapes and false reliance on runtime type checking will cause these bugs. Inter-service communications require IO validation on both sides. If you have an UI talking to an API, both sides need to validate their input. These bugs occur when developers are not assured of their IO. They have these symptoms and are caused by these errors when using these tools. Thank you. That's my presentation.
Nice.
That was excellent.